how reflection and rotation make one group?
They don't make group. I'm saying we have a group which is this, as you can see on your screen. Okay, this is a group. I was explaining how this is a group, how this is a group. So to explain how this is a group, the thing that I explained here is, if you take equilateral triangle and first you apply this kind of reflection and then you apply rotation, then you will get some result. By some result I mean, if you start with an equilateral triangle, say ABC, okay, so sigma prime is reflection like this. So sigma prime will make 1 go to 3 and 3 go to 1. So sigma prime is reflection like this, like this. So I think after applying sigma prime, I'm not sure, I think I should get like this, C A B, and then we have to apply rotation on that. So if we apply rotation, R takes it like this. So what should we get? If R takes it like this, I'm getting A C B. So this is my result. Okay, now let us apply sigma double prime. So this is my triangle ABC I start with, and apply sigma double prime, and let's see, sigma double prime is reflection about this. So reflect about this. So I should get oh, A B C. I think I made a mistake. Okay, R is rotation by 2 pi by 3. In which direction? R is rotating in anti-clockwise direction. So yeah, I rotated. Okay, there is some mistake here, but what I want to say is that when you apply R and sigma prime on the triangle, you get the same result by applying sigma double prime on the triangle. So but find where I have done mistake. So I started with the triangle ABC, I applied sigma prime. Sigma prime is reflection. This is sigma prime reflection. If I reflect, does it become like this? Yes, CB, and then there is a rotation. Okay, I made a mistake here. No, sigma double prime is here, so I should get ABAC, and here I'm getting ACB. Vikram, can you find the mistake? Try. Just first apply sigma prime, then R. So sigma prime will make this 3 and this 1, and then R will rotate it, and then this will become 1, and this will become 3, this should become 2, and sigma double primes will make this 1 and 2. I think we misunderstood reflection. I was when I'm reflecting, I'm permuting the indices. Should I do that? I don't know.
Are you sure it will be sigma double prime? It
Yes.
seems to be sigma.
No, it has to be sigma. Okay, yes. Okay, let us make it instead of what did I do? R sigma. Yeah, it is written sigma double prime. R sigma will go to sigma double prime, and sigma R goes to sigma prime. Alam, you check how sigma R goes to sigma prime.
Okay. Sigma R results in sigma second, sigma double prime.
Sigma R. No, I'm getting sigma R is sigma prime. Let's see how. So we need to do this. So say I have this triangle A, B, C. Now I apply what I need to do. I'm doing sigma R. So first I apply R. If I apply R, then it will make a rotation in this direction. I should get equilateral triangle C, A, B. And then I apply sigma. Sigma is symmetry around this. This is sigma. So this will become B, A, C. Okay. Now let us A, B, C, and sigma double prime is along which direction? No, sigma prime. Sigma prime is like this. So this is sigma prime, right? So if I reflect it, I should get A here, C here, and B here. So you see the result here and here matches. So sigma R is equals to sigma prime. Okay.
Okay.
This is clear. Now similarly, if you do R sigma, he is saying that you will get sigma double prime. Okay. So try doing R sigma in this way. So let me do it. So R will make it like this. R sigma means first you apply sigma and then R. Okay, let's try. So this is A, B, C. First I apply sigma. Sigma is like this. So I'll get A, and here B, here C, and then I will rotate like this. So it will become B, A, C. Okay, so this is my R sigma. Now check sigma double prime. Let's see sigma double prime. Sigma double prime goes like this. So if yeah, we got it. So if I do sigma double prime, then I'll get BAC. Yes, it's correct. If you have any doubt, or I should proceed, I think this is clear.
It's okay.
It's okay, right?
Yeah.
So this is it. So why I proved this to show you that this interesting result. Let me make it red. This result tells you that this is a non-abelian group. So if it would have been an abelian group, if all the elements would have commuted with each other. Here you can see R and sigma, they don't commute with each other. Hence it's a non-abelian group. Okay. Should I proceed?
Yes.
Okay. Okay. So, okay, Vikram. So start recording, and Alham also. You can also start recording after I say. Just 1 minute.
I recorded when you start.
Okay. Just give me some time. Let me note it down. CV is equals to RW sigma prime sigma double prime. Okay, so today's class start from here. So subgroups. So what did we understand from the last class? We saw that from the last class we constructed a group. We named it C3V, and inside the group you had elements R, rotation, this is also rotation but in a different direction, identity, and 3 reflections, sigma, sigma prime, and sigma double prime. Now what you can see from here that this is a non-abelian group, as I said, and I also proved non-abelian because we saw that if you apply R sigma on the equilateral triangle, and if you apply sigma R on the equilateral triangle, then you don't get the same result. Hence it's a non-abelian group. Now once we have a non-abelian group, and then we also showed that yeah, I think this is it. We did this. Now subgroup is you can make certain groups out of it. So let me make one called a C2. I make C2 by just keeping these elements E and sigma. So this is a group by itself. You can check it. How? If you multiply sigma and E, you get what? You get sigma. And if you apply sigma square to the equilateral triangle, I think you will get identity. Let's give a check. So this was my triangle A, B, and C, and I think sigma was in this direction. So if I apply sigma once, then the triangle will become A, C, B, and if I apply sigma twice, then again I'll make a reflection here, then I get A, B, C. So as you can see that sigma square gives you the same triangle as the triangle itself. So that's why there is a E here. So this is a subgroup. Why it is a subgroup? Because it is a group and this group is contained inside a larger group, and that's why it is called a subgroup. So C2 is a subgroup. So let me write it sub here. Similarly, I can construct one more subgroup which is I should name it C3 because there are 3 elements with identity, R, and omega. And remember there was a constraint, omega is equals to R squared, that you can check on the triangle. So this is a subgroup. This is also a subgroup because it is a group by itself and it is a part of a larger group. So it is contained in a larger group and hence the word sub. Okay. But you can see if I form a group with sigma, sigma prime, and sigma double prime, this is not a subgroup. One reason it is not a subgroup, you can see easily that it does not contain identity element. So this is a quick check that this doesn't form a subgroup. Okay. Now the idea of subgroup is clear. Now we will jump to representation. So representation of group. So when you read about representation of group, what does it mean? Okay, on a for a simplest example, you can represent group elements So we are, when I say representation of a group, it means representation of group elements. So you can represent group elements using matrices. Okay, let's look at an example how we can do that. Remember the last group, so C3V, it had your E, R, W, sigma, sigma prime, sigma double prime. Now I know there are operations. What kind of operations I know? I know that if I square the R, I get W. I know that if R is acted with sigma, I get sigma double prime. I also know that if sigma is acted with R, I get sigma prime. So these are the known things that we have in the group. So we know that if I multiply any two elements, then this element belongs to the group. So if I multiply any two elements, it belongs to the group. But here in this case, we exactly know which element it belongs to. This is very important. You should have an exact idea when you multiply two elements of the group, what is the exact element in the group that you reach. Using this idea, you can actually construct matrices. For example, what I'll do is I will do matrix representation. Let's do it in the next page. So we have matrix representation. So this is part of a representation. There can be many other representation, but here we are doing matrix representation. So E was identity element, and we will do so E is an identity element, and if I'm gonna make a matrix out of it, I'm gonna represent it by D, and many people write a 2 here to show that we are going to do a two-dimensional representation. And tell me what will be the identity matrix. So it will be 1 0 0 1. Okay. Similarly, let me make a matrix out of the R. So this is gonna look like it's gonna be 1 by 2, and it is a two-dimensional matrix. So there will be elements here, minus root 3 here, root 3 here, and minus 1 here. Okay. Then let me make a matrix representation of the reflection, and this will be minus 1 0 0 1, and let me make a matrix element out of sigma prime. This turns out to be 1 by 2 1 root 3 minus 1, and then last the matrix representation of the group element sigma double prime, which is 1 by 2 1 minus root 3 minus root 3 and minus 1. Now you can easily check that if you make the matrix representation of all the group element in such a way, then all the properties that I wrote earlier, for example, we know that W is equals to R square. So now you square the matrix R and see you get W or not. So for example, I get 1 by 4 and the matrix minus 1 root 3 minus root 3 minus 1, and then multiply with itself, minus 1 minus root 3 minus 1, and you should check that you will get the matrix representation of W. Did I mention? No, I have not written W, so let me write it. So matrix representation of the element W turns out to be 1 by 2 minus root 3 and minus 1. I hope I made it correct. Let me give a quick check. Yes, this is correct. Then this is correct. This is also correct. Yes. Yeah. So you can do this multiplication and check it out for yourself whether you get it or not. Okay. So you'll get W. So similarly, if you now
for writing the matrix for sigma prime and sigma double prime, you use the relations R sigma equals to sigma double prime and sigma R equals to sigma prime.
yes, you have to remember all the relation and you have to guess the matrices. Now you will say that how was I able to write all the matrices? There should be a way to form these matrices. You cannot guess such complicated things, right? So we will come to that, how to make matrix representation. But all I'm saying here, the information that I wanted to convey in this particular thing here is that if you have group elements, then if you know the operations of the group elements, that if you multiply two group element, you exactly know which group element you are going to end up with, then you can represent those group elements using matrices. And these matrices should satisfy the same relation that the group elements were satisfying. That means when I wrote that R sigma is equals to sigma double prime, then when I make a representation out of them, then I should make sure that the representation of R and the representation of sigma, when I multiply them, I should get the representation of sigma double prime. That's the main idea. Okay. So this is clear, right? So we can make matrix representation of group elements. Okay, this is just a mathematical convenience. So working with matrices, okay, we can do a lot of things if we do mathematical representation of abstract things. So till now, R sigma, sigma double prime had no mathematical things connected to them. Okay, we just saw them as letters multiplying with each other, and we saw them as operations. But now we have mathematics related to these group elements. That is, we have represented them by matrix elements. Okay. Now here I want to convey one more interesting thing, that all the matrices that I have used in the above representation, these all matrices belong to O2. So all matrices used above, they belong to O2. Now here you will get a clear idea of what O2 is. So O2, when I write such kind of things, O2, you should remember this is a set of elements. Okay, I told you O tells you what kind of elements you have, and 2 tells you the dimension of representation. So let me tell you, O2 is nothing but set of matrices, or more precisely, it is a set of 2 cross 2 matrices such that, so consider an element O, which is a 2 cross 2 matrix, belongs to O2. Then for any O transpose O should be 1. If this is the condition, if a 2 cross 2 matrix satisfies this condition, we say that the matrix belongs to O2 set. Okay, so let us we can make a quick check. Just take any one of the matrix, form the transpose and multiply with each other. Let's see, a simplest example will be use D2 sigma. So what was D2 sigma? D2 sigma was -1 0 0 1. And what will be the transpose of D2 sigma? Let's make the transpose. You'll get -1 0 0 1. So it seems the transpose is same. Now do this, D2 sigma transpose D2 sigma, and what you will get. Oh, are we getting 1? Yes, we should get identity matrix. Okay, so when I wrote 1, this 1 means 2 cross 2 identity matrix. So it means 2 cross 2 identity matrix is represented by capital I. So when you read, remember when I was talking about U1, I said U1, whenever you look at U1, you should consider this is a set of elements. What kind of element? I said that the elements were looking like this, e to the power I theta. And for various theta, you have various element. And this is a one-dimensional object. That's why there is a 1 here. And U represents that the elements have a certain look. Now, when I wrote O2, you should remember that O2 means it is a set of elements. Here, the elements were 2 cross 2 matrices. They look different from the U1. Okay, these are matrices, and the matrices are 2 cross 2. That's why there is a 2 here. And then they satisfy a special condition that any matrix O which belongs to this set, if you take its transpose and multiply with itself, you should get the identity matrix in 2 cross 2. That's the whole idea. Okay, so that means you are mapping group elements from the group to matrices. So for example, remember, if I can do this, so I have a map phi, and this map takes you from group elements and puts you into the matrix representation, matrix group. So here I can write O2. But the question is, we don't know what the map is, right? We know which element go to what element of O2, but we have no idea how to form the map. Okay, and we will take a look at this in the next lecture. Till here, I think it is clear. Okay, now if I want to give a more precise definition, then the map phi in a general definition. So let me make it general. In general, the map phi takes all the group elements and puts it into GLV. Now what does it mean? GL means general linear group. It is a group of all matrices, or I should say it contains matrices. So this is the general definition of that says that you are taking group elements and you are identifying group elements with certain matrices such that the group operations are also satisfied by the matrices. Okay, so let me write the definition of what do you mean by representation of a group. So it goes like this. A representation of a group G, so G is our group, on a vector space V over field F. I'm going to explain this now. Over field F is a group homomorphism. Is a group homomorphism from the elements of the group G to GLV. Now before explaining this, let me tell you, remember what we did just before. In the before cases, all the matrices that we used were of this form, and D2, and let me write, instead of writing group elements, let me write the C3V to represent the entire group. And this was the matrix representation, and this matrix representation was done over the vector space R square, and the field is R. Okay, now what do you mean by that? So if you take any group representation, so for example, when you look at D2 sigma prime, so D2 sigma prime was 1 root 3 root 3 minus 1, and whole thing was multiplied with half. You see that each element of this matrix, it belongs to the real number, yes or no? It belongs to R, and this is 2 cross 2. So such kind of matrices, if they act on a column vector, then the column vector will be like this. So it will be 2 cross 1. Okay. So some more clarity is required here regarding this vector space. So why do we have a vector space entering into the definition of group representation? So till now we understood group representation as, okay, you have a set of elements in the group and you make the corresponding matrices such that the matrices satisfy the same operations that the group elements will satisfy. But now all of a sudden when I wrote the definition, I'm talking about a vector space V, a field F upon which the entire stuff is built upon. Well, now comes the interesting thing. Whenever, just remember, when we build a representation of group elements G, so whenever we build it over a vector space. We build it over a vector space. Okay, what does the meaning of this sentence? Okay, now it's very easy. Now we all know the definition of vector space, right? So the definition of vector space is known, but what is the most interesting thing about a vector space? The most interesting thing about a vector space is the basis. So every vector space contains basis. Okay, so what is a vector space? Anybody remember the definition? So vector space, anybody, can you check out the definition quickly? I'm going to give a quick review of vector space in 2 minutes. Okay, so that to brush up your knowledge. So let me quickly check vector space definition now. So vector space is a space which consists of vectors, and you can do operations like commutative operation, addition of vector, associative, distributive, etc., etc. So let's not go to all the technical stuff. Just let me write it as a vector space is a space which consists of vectors. Okay, let me give you an example. Consider a space of R2. So by R2 I mean a two-dimensional flat Euclidean space. So this is X, this is Y. Now any point here, so consider a point here 2, 3. Now if you have a point on R2, then you can always draw a vector R, and you say that your R vector is actually 2i and 3j. Yeah, this is how you made vectors in 2D space. So now we are going to represent it in a very simple way. R vector is 2, 3. I'm going to write it like this for my convenience. So whenever I write R as 2, 3, it's a vector. Similarly, I can have another vector R1 as 3, 4. Similarly, I can have another vector R2 as say 1, 6. So in this way, I'll have, I think, infinite amount of vectors in 2D space. Yes or no? So if I have so many vectors, now what is the basis? I say that we have two bases here, 1, 0 and 0. Why these are bases? Basis means minimum set of vectors you need inside a vector space such that using the linear combination of the basis, you should be able to form any vector in the vector space. And I am saying that 1, 0 and 0, 1 is the basis of R2 and it is sufficient. Let me give an example. So can I form the vector 3, 4 using the basis? Yes, I can easily construct. If I have 3 coefficients multiplied with the first basis and the 4, which is a coefficient multiplied with the second basis, I'll get 3, 4. So in this way you can construct any vector in the Euclidean 2D space using basis. So this is our basis. So we need 2 bases. If you just have 1 element here, it's not possible. Similarly, you can go to 3D. In 3D, you need 3 bases. They are 1, 0, 0, 0, 1, 0, and 0, 0, 1. And using these bases, you can construct any vector in 3D. So, okay, so we understood vector space. Now the question is, I said that we use vector space to build a representation. So when I say we use vector space, more precisely, I mean to say we use the basis. What I said, we use the basis. So now we are going to use basis and form representation of group. Okay. Okay, how do we do this? Consider a group. Let there be a group, and the group has 2 elements, E, which is identity, and inverse, which is I. So what does the E and I does? So E and I, they act on coordinates. So previously we had our group elements acting on the equilateral triangle, and now we have a group elements which act on the coordinates. For example, let's work in 1 dimension. So 1 dimension means we have only x axis. So how does the group work? So if the E acts on an element x, then you get x. But if O acts on an element x, you get not O, it is I. So if I act on an element x, you get minus x. Okay, so this is how the group elements, they act on the coordinates. Okay, so now we can do a very interesting thing. If E and I act on coordinate, and suddenly if I have function, we know that in our world, if you have coordinates, then you can always define functions on the coordinate. So consider a function psi of x. So tell me, if E makes the coordinate go from one to another, which is the same, then we should have some operator associated with the group element, and let the operators are represented by OE. So these operators which are linked with the group elements, they act on functions. So here I'm gonna get psi of x. So what did I say? I say that for every group element which act on, so the group elements are acting on coordinates, we have operators, and where do these operators act? These operators, they act on functions of the coordinate. So let me just write function. As you can see here, I gave one example. If OE acts on psi of x, we get x. Okay, so if I consider another function, say psi of minus x. So if OE acts on psi of minus x, what do I get? I'll get the same, psi of minus x. Okay, so now consider the basis. So I'm saying that here, say psi of x and psi of minus x, they are bases. So I'm claiming that these two elements are bases, and using the linear combination of this, you can form a space of functions. So you can, using this basis, you can form a space of functions. Okay, space can be anything. It can be a space of vectors, it can be a space of functions, doesn't matter. So now using this basis, I'm going to make a matrix representation of this operator. Let's see how. So first act the operator E on the basis psi of x and write it. What do we get? We get psi of x. That means I can write it as 0 multiplied with psi of minus x. So what is this? This, you can see that I am making a linear combination of bases that is giving me this function. Okay, so this is some function psi prime of x. Okay, so not to get confused, I'm going to remove this and I'll discuss this later. Now similarly, let me act my operator on psi of minus x and write the result as a linear combination of basis functions. So this will be 0 into psi of x plus, we know that we are going to get psi of minus x. So if using this basis, if I'm to form the matrix representation, then I say that matrix representation of E is going to look like 1, 0, 0, 1. And how did I form? I formed it from here by using the coefficient. The coefficient here is 1, the coefficient here is 0, here is 0, and here is 1. So using the basis, I formed matrix representation of the element E. Okay, now let's do the reverse. Now let us check that this is a correct way of denoting. So let the matrix representation of my group element act on the basis. So the basis was psi of x and psi of minus x. So when you do this, you should make sure you get the correct result, and yes, you get the correct result. What do you mean by correct result? The meaning of correct result is when you multiply the matrix with this. For example, we have 1, 0, 0, 1 multiplying with psi of x and psi of minus x. Then what do we get? We are going to get psi of x and psi of minus x, which is quite natural, right? So when your group element act on the basis, this side what you should get is given and is correct. Now let us look at one more example that we left out. We had one more operator like the inversion. So when the I was acting on the coordinate, we get minus x. That means I can form an operator. So let me write it as OI act on the basis. So consider when OI act on psi of x, we get psi of minus x, and when OI act on psi of minus x, we are going to get psi of x. This is the result. Now write this result as a linear combination of the basis that you have chosen. So let's do that. So OI when acts on psi of x, in terms of basis, I don't get psi of x, but I do get psi of minus x. And when OI acts on the basis psi of minus x, I get psi of x because minus x goes to x, and I don't get this one, so I write a 0 into psi of minus x. So using this basis, now I can form a matrix representation of I, which is 0, 1, 1, 0. And as usual, as I said earlier, you can give a quick check that when you have the matrix representation of your inverse operator and you act on psi of x and psi of minus x, on the other side you should get the correct result, which you are getting. Here you will get psi of x, and here psi of minus x, and here you will get psi of x. So as you can see, there are 3 steps. Step number 1, the group elements, they act on the coordinates. Second, depending on how they act on coordinate, we formed group operators that act on the function. And if you have the basis of function, if you choose some basis, then using the basis you can form the matrix representation of these operators, DE and DI. So if you have an operator, so which is operator? Here we have the operator. So if you have the operator and if you have a vector space, then find how the operator acts on the basis, and depending on that you can make the matrix representation. Now question is why we do this. Okay, that's the question. Now before continuing, do you have any doubts?
No.
No. So I would like to end the class here for 10 minutes, and I'm going to send you the this one, and I want you to read it again before we continue. Okay, I think that will be better. So I'm going to give you maybe I think Elham's class, so let's do it after her class. Okay, so let's end it here.